Good evening and welcome to the Dreamtime Discoveries. Tonight's journey is a gentle one, and you're invited to let the world slow down around you. This video is designed to accompany you as you unwind, whether you're curled beneath blankets or simply letting your thoughts drift into the quiet. Our theme this evening is infinity, that elusive concept which slips through the fingers of mathematics, philosophy, and physics alike. Before we begin, I would love to know where in the world you are listening from. It is always fascinating to imagine these words floating across time zones and landscapes to reach you. If this video helps you relax or sparks your curiosity, a like and a subscribe would be a kind way of supporting the channel. I sometimes worry that these stories may become so interesting they do the opposite of their purpose, keeping you wide awake. But then again, if you do stay up, at least you will drift off with new wonders of the universe in your mind. Let us set sail into tonight's subject. What does it mean when something has no end? Infinity is a word that seems simple, yet when studied closely, it becomes one of the strangest ideas humans have ever grappled with. From the endless steps of a paradox to the possibility of a universe that stretches forever, infinity rests at the border between imagination and science. It has been both a guiding light for discovery and a stumbling block for understanding. For as long as people have looked up at the night sky, they have wondered whether the stars continue on without limit. Philosophers puzzled over the infinite centuries ago, trying to reconcile it with motion, with space, and with the flow of time. Mathematicians later found that infinity could be written into the language of numbers, though it introduced puzzles as well as answers. And physicists today still wrestle with the idea, often finding that equations slip into infinity, where reality itself refuses to follow. Infinity touches every corner of thought, the structure of space, the ticking of time, the energy of particles, even the question of how many worlds or possibilities might exist. It is a concept that refuses to be contained, as much a mystery as a tool. This is why it is both feared and cherished by scientists. Without it, our equations might be smaller, but with it, our universe is immeasurably larger. In the chapters ahead, we will wander through infinity's many faces. From ancient paradoxes to modern physics, from the infinitesimal to the endless expanse of the cosmos. Along the way, there will be puzzles that delight, curiosities that confuse, and ideas that calm with their vastness. Infinity is not something you can hold in your hand or even picture clearly in your mind. And yet, it has a way of shaping how you think about everything. Tonight, let it unfold slowly, like the horizon receding into a quiet sky. Because once you begin to ask what infinity means, you find yourself in a journey that may have no end. Infinity is one of those ideas that seems so simple when you first say the word, yet it quickly grows slippery and strange when you try to think it through. For as long as human beings have been gazing upward at the sky or looking inward at their own thoughts, the notion of the endless has been a companion. Long before modern physics, people wrestled with the concept of something that has no limit, no boundary, no final step. The ancients did not have telescopes, particle accelerators, or chalkboards filled with symbols. Yet they had imagination, and with it came some of the first attempts to grapple with infinity. The Greeks in particular loved to push ideas to their extremes. One of the earliest figures to make infinity famous was Zeno of Elea, a philosopher who lived in the 5th century before the Common Era. Zeno is remembered less for giving comforting answers and more for presenting maddening puzzles. His paradoxes were designed to make people question their assumptions about motion, space, and continuity. In one of his best-known examples, he argued that to walk across a room, you must first travel halfway. Then, before you finish, you must cover half of the remaining distance, and then half of what is left after that, and so on without end. If this is true, then logically you would never actually reach the other side, since there would always be another half step remaining. Of course, in practice, people do reach the other side of the room, but the paradox highlights the strange tension between the infinite, divisibility of space, and the finite nature of motion. Another of Zeno's paradoxes involves Achilles, the legendary Greek hero racing against a humble tortoise. Zeno argued that if the tortoise were given even a small head start, Achilles could never catch up. Why? Because by the time Achilles reaches the point where the tortoise once was, the tortoise has already moved a little further ahead. By the time Achilles reaches that new spot, the tortoise has again advanced. The chase, according to the logic, is endless. Clearly, anyone who has seen a tortoise attempt to outrun a sprinter knows that reality has other plans. But Zeno's point was to show that infinity hides within the simplest acts of motion. These puzzles were not meant to paralyze people, but to challenge the very foundations of how humans thought about the world. The Greeks were not alone in dreaming about the infinite. In India, ancient thinkers developed the idea of kalpas, vast cycles of time in which the universe is created, destroyed, and reborn in endless succession. These cycles were not counted in years or centuries, but in unimaginable spans that made even the longest human dynasty seem like a blink. A single kalpa was said to last longer than it would take to wear down a mountain if you brushed it with a silk cloth once every 100 years. The metaphor is almost whimsical, but it is also deeply profound. The universe is a grand rhythm of endless creation and dissolution, far beyond the grasp of an individual life. Chinese philosophy, too, engaged with the notion of endlessness. The Tao described in Taoist thought was often seen as eternal and boundless, a principle that underlies all things without beginning or end. The Tao Te Ching, attributed to Laozi, speaks of the Tao as something that cannot be fully named or defined precisely because it is limitless. This is not infinity in the mathematical sense of numbers marching toward the horizon, but rather infinity as a quality of existence itself and endless, unfolding that resists confinement. The Babylonians and Egyptians, who observed the sky with great care, also brushed against infinity in their cosmologies. The endless dome of stars suggested a space without limit, while the cycles of the Nile, or the return of the seasons, gave rhythm to a sense of eternal recurrence. In these ancient worlds, infinity was not an abstract equation, but a lived experience. The endless flood, the eternal night sky, the perpetual cycle of day following night. It is striking how different cultures often return to the same question. Does the universe have a boundary? To imagine a wall at the edge of the cosmos raises an immediate puzzle. What lies beyond it? If there is something beyond, then the universe is not truly bounded. If there is nothing, how can nothingness itself have an edge? The human mind is unsettled by the idea of an end, but equally unsettled by the thought of no end at all. Infinity always sits at this uneasy border. Even in mathematics, the ancients were aware of infinity's peculiarities. The Greeks distinguished between potential infinity and actual infinity. Potential infinity was the idea that you can always add one more to a number or divide a distance again and again without end. Actual infinity, by contrast, was the existence of infinity as a completed whole, something that truly exists rather than just being approached. Aristotle in particular rejected actual infinity, believing it could not exist in reality, but only as an abstract notion. He thought infinity was always a process, never a final state. This distinction still echoes in modern thought. When you count numbers, you never arrive at infinity. You simply move endlessly forward, each step revealing the potential to keep going. Infinity is not a destination at the end of the road, but the road itself stretching without limit. For the ancients, this was both a comfort and a torment, depending on how one chose to look at it. Religious traditions also embraced infinity, often as a way of describing the divine. The gods, after all, were thought to be eternal, boundless, and limitless. In many traditions, Infinity became a marker of the sacred something beyond human reach, yet intimately tied to human longing. To call a deity infinite was to say it was beyond decay, beyond time, beyond measure. The infinite became the perfect counterpoint to the finite nature of human life. What unites all of these perspectives is the fascination with the endless. Whether through paradoxes of motion, cycles of cosmic time, eternal principles of nature, or mathematical debates about actual versus potential infinity, early thinkers could not resist the allure of the infinite. They pressed against the boundaries of human thought, only to find that the boundaries themselves seemed to dissolve into the horizon. It is almost amusing to think how long ago these puzzles were first posed, and yet they still hold power today. The tortoise still teases Achilles, the half distances still await the walker, and the mountain of the Kalpa still endures its silken brushing. The ancients may not have had the modern language of physics or mathematics, but they were right to see infinity as a place where reason both falters and expands. In their own way, they handed us the first maps of the endless, not maps that give a clear destination, but ones that invite us to wander. Because in every culture that dreamed of infinity, the idea was not just a puzzle to solve, but a horizon to approach, forever receding, forever calling the human imagination to chase after it. Asterisk. Numbers have a peculiar way of carrying infinity quietly inside them. You only have to start counting to see it appear. 1, 2, 3, 4, 5, ... And there is no stopping point. However far you go, there is always another number waiting patiently beyond. Children discover this at an early age, asking adults the impossible question of what comes after the biggest number. The only honest answer is that there is no biggest number. Numbers are like stepping stones across a river that has no opposite bank. You can keep moving forward endlessly, with infinity always receding just out of reach. This kind of infinity is called potential infinity. It means there is no final stop, but also no actual point you can touch and declare as infinite. You cannot place a crown on top of the number line and say, "Here lies infinity." Instead, it is the process itself that is endless. Each new step only creates the potential for another. It is a kind of infinity that feels natural, even friendly, since we are so used to adding, subtracting, multiplying, and imagining larger and larger totals. Yet once you scratch the surface, even the simplicity of counting begins to reveal some surprises. Take even numbers and odd numbers, for example. Intuition might say that the collection of all whole numbers is larger than the collection of just the even ones, since the evens are only half of the list. But infinity plays by stranger rules. For every whole number, you can pair an even number. 1 pairs with 2, 2 with 4, 3 with 6, and so on forever. This one-to-one matching shows that the set of even numbers is not smaller at all. It is exactly the same size as the set of all numbers, at least in the infinite sense. The same is true of odd numbers, square numbers, or prime numbers. All of them stretch on without end, and all of them can be paired neatly back to the original list. Infinity does not shrink just because you remove some of its parts. This strange elasticity of infinity puzzled mathematicians for centuries, until the 19th century, when a German thinker named Georg Cantor decided to take it seriously. Cantor did not shy away from infinity as many before him had done. Instead, he studied it head-on, and in doing so, he revealed that not all infinities are created equal. To most people, infinity is simply endlessness, one indistinguishable ocean. But Cantor showed that there are different sizes of infinity, a discovery so bold that many of his contemporaries resisted it fiercely. Cantor's first insight was to compare different sets of numbers. Whole numbers 1, 2, 3, and so on form what is called a countable infinity. You can imagine listing them in a line, matching each number to its position on the list. But what about fractions? Numbers like 1/2, 2/3, or 27 over 99. At first glance, the set of fractions seems much larger, since between any two whole numbers, you can squeeze infinitely many fractions. And yet, Cantor proved that even fractions are countable. With a clever diagonal method, he showed you can list every fraction without missing one. Pairing each to a natural number dot, then came the leap. What about real numbers? The numbers that include not just fractions, but also the messy decimals that go on forever, like the square root of 2 or pi. Cantor discovered that these real numbers form an infinity too large to be listed. No matter how you try to organize them, some will always slip through your net. This was shocking. It meant there was more than one kind of infinity. And the infinity of real numbers was strictly bigger than the infinity of whole numbers. Cantor called these sizes cardinalities, and the infinity of the real numbers he named the continuum. This was not just mathematics, but philosophy reshaped by numbers. Infinity was no longer one idea, but a tower of possibilities, with each level dwarfing the one below. Cantor's work faced harsh criticism, even ridicule, but over time, it became one of the cornerstones of modern mathematics. Today, his discoveries underpin set theory, the foundation upon which much of mathematics is built. To get a taste of how strange infinity can be, imagine checking into Hilbert's Hotel. This thought experiment was devised by the mathematician David Hilbert to illustrate the paradoxical hospitality of infinite sets. Picture a hotel with infinitely many rooms, numbered 1, 2, 3, and so on. Even if every single room is full, a new guest can still be accommodated. How? Simply move the guest in room 1 to room 2, the guest in room 2 to room 3, and so on down the line. This frees up room 1 for the newcomer, and despite the reshuffling, everyone still has a bed. Things get stranger. Suppose an entire bus of infinitely many new guests arrives. No problem. Move each current guest from room N to room 2N, doubling their room numbers. Now all the odd-numbered rooms are vacant, and there are infinitely many of them, ready to welcome the infinite busload. In fact, no matter how many infinite crowds arrive, the hotel always finds a way to squeeze them in. Infinity seems endlessly accommodating, a host that never has to turn anyone away. But the paradox has another side. Try checking out of Hilbert's Hotel, and the strangeness grows. If everyone leaves except the guest in the first room, the hotel still contains infinitely many occupants. If guests in every second room leave, infinity remains. Subtracting infinity from infinity is not like subtracting ordinary numbers. It produces results that depend entirely on how the subtraction is done. Infinity is generous, but also mischievous, refusing to obey the rules we expect. All of this reveals the slipperiness of numbers without end. When you're dealing with finite collections, logic is straightforward. Remove half of 10 apples, and you're left with 5. Add 10 apples to an empty basket, and you get 10. With infinity, the rules bend and twist. Halves can equal wholes, and subtraction may leave you right back where you started. What feels like nonsense at first is simply the peculiar landscape of endless quantity. For mathematicians, these insights are not just intellectual games, but essential tools. Calculus, for instance, rests on the idea of infinity. When calculating the slope of a curve, you imagine shrinking a step smaller and smaller, approaching an infinitely small limit. The result is not infinity itself, but the shadow of infinity at work. Similarly, infinite series, endless sums of numbers can converge to a finite value. Add 1/2 plus 1/4 plus 1/8, and so on forever, and the total approaches 1. Infinity hides in these processes, yet it delivers finite answers. There is something quietly humbling about all this. Infinity in mathematics is both strangely playful and deeply profound. It shows that our most basic tool numbers contains depths we can never exhaust. Start with simple counting, and you soon stumble into a hotel that never fills. A ladder of infinities, climbing into the unknown, and paradoxes that defy common sense. The ancients may have wondered whether infinity could truly exist. But by stepping into the world of numbers, humanity discovered that it was not just an idea hovering above us. It was built directly into the logic of counting itself. Every time someone asks what comes after the biggest number, they're already brushing against the endless. Numbers are a reminder that infinity is not some distant concept at the edge of the cosmos. It is right here, embedded in the most ordinary act of saying, one more. Time is the quiet river that carries every life forward. Yet, it may be the most mysterious dimension of all. It slips past without effort, relentless and smooth, leaving us with memories of what has gone and expectations of what might come. When people began to wonder about infinity, they naturally turned their attention to time. Could time itself stretch endlessly backward into the past? Or does it have a beginning? Will it extend forever into the future? Or is there a final moment waiting like a hidden wall? These questions strike at the heart of what infinity means, not only for physics, but for our understanding of existence itself. Many ancient traditions imagine time as a cycle rather than a line. To the Babylonians, Egyptians, Indians, and Greeks, the eternal return of the seasons, the rising and setting of the sun, and the birth and death of generations all suggested a wheel turning endlessly. In Indian cosmology, time was measured in immense cycles called yugas, with ages of creation and destruction rolling into one another without limit. The Greeks had their own version, eternal recurrence, the idea that the universe endlessly repeats itself. In this vision, the future is not new, but a repetition of what has already happened over and over again without end. Philosophers have long debated the possibility of infinite regress in time. If every event must have a cause, and every cause has a cause before it, then where does it all begin? Does the chain of causes stretch back forever? Some argued that it must, since every attempt to find a first cause only pushes the question further. Others believed the infinite regress was impossible, and that time must have a definite beginning. Aristotle leaned toward the idea of eternal time, reasoning that it was impossible for something to come out of nothing. Centuries later, Christian theologians argued for a creation at a specific point, a moment when God brought time and the universe into being. Modern science eventually took its own stance. With the rise of cosmology in the 20th century, evidence began to point strongly toward the beginning of time, the Big Bang. According to this picture, about 13.8 billion years ago, the universe expanded from a state of extraordinary density and heat. It was not an explosion within space, but the expansion of space and time itself. The Big Bang model implies that time as we know it had a starting point. Before this, asking what happened earlier may not even make sense, since time itself was born in that event, and yet the debate is far from settled. Some cosmologists have proposed that the Big Bang may not have been the ultimate beginning, but rather a transition. There are models in which the universe bounces, collapsing under its own gravity, and then springing outward again, with cycles repeating endlessly. In these scenarios, time stretches backward infinitely through countless previous universes. Others imagine eternal inflation, where new bubble universes constantly form within an ever-expanding space-time. If so, our own cosmic history may be just one chapter in an infinite story. The infinite future is just as puzzling. If the universe continues expanding forever, then time too will continue without bound. Stars will eventually burn out. Galaxies will drift apart, and the cosmos will slide into a cold, dark state of near silence. Physicists call this the heat death of future, where energy is evenly spread and nothing new can happen. It is an infinite future, but not a lively one. On the other hand, if dark energy behaves differently than expected, the expansion might accelerate so violently that galaxies, stars, planets, and even atoms are eventually torn apart. This big rip would be a catastrophic ending, not an infinite continuation that our own lives provide a smaller reflection of these great questions. To each person, time feels like a straight arrow, moving from birth to death. Yet history as a whole suggests endlessness. Civilizations rise and fall, but humanity continues. Generations pass like waves on the shore, yet the ocean of time does not dry up. We experience a finite slice of it, but we cannot help wondering whether the river itself has a source or a mouth. Eternal recurrence adds another twist. The philosopher Friedrich Nietzsche, inspired by earlier Greek thought, asked us to imagine that every event in our lives will be repeated forever, exactly as it has happened. Every joy, every sorrow, every small choice looping endlessly through time. It was not necessarily a scientific claim, but a philosophical challenge. Would you embrace your life if you knew it would recur infinitely? Infinity here is not just a question of physics, but a test of perspective. Physics brings its own paradoxes. If time is infinite, then events that are highly improbable may still be guaranteed to happen eventually. For example, in an infinite span, every possible configuration of matter could occur. There might be another Earth with another version of you living almost the same life, except perhaps tonight you chose a different bedtime story. While this stretches imagination to its limits, it also raises serious scientific puzzles about probability and meaning in an endless timeline. And yet, despite all of these possibilities, time retains its silence. We cannot step outside it to see whether it has an edge or a loop. Every clock ticks forward, every memory looks backward, and the rest remains hidden. Scientists build models, philosophers weave arguments, and poets imagine eternity. But the truth may remain just beyond the horizon of what we can ever measure. What we can say with certainty is that time, whether infinite or finite, gives shape to our experience. Without it, motion, change, and life itself would have no framework. The mystery of whether it stretches forever or began with a single spark does not diminish its role. Instead, it adds to its wonder. Time is not simply a sequence of numbers on a clock, but the stage on which the play of existence unfolds. Perhaps the most beautiful thing about the infinity of time is that we will never exhaust it as an idea. Even if the universe has a beginning and an end, our minds can still imagine beyond them, picturing what lies before the first dawn or after the last night. Infinity in time is both a scientific hypothesis and a canvas for imagination. It reminds us that while our individual lives are brief, they take place within a mystery so vast it cannot be contained by beginnings or endings. Whether time proves to be an endless road or a circle returning upon itself, it will always carry us forward step by step. To ask whether it has boundaries is to stand on the edge of comprehension itself. And in that silence where certainty fades, the imagination finds room to dream. Asterisk. Look up at the night sky on a clear evening, and you're staring into one of the oldest questions in human history. Does it ever end? Are the stars scattered across an infinite canvas stretching on forever? Or is the universe merely vast, with a boundary that curves back on itself? This question has teased astronomers, philosophers, and dreamers alike for centuries. The idea of infinite space is both thrilling and unsettling. It suggests a reality so large that every direction leads endlessly outward, with no walls, no edges, and no stopping point. Yet, there is another possibility, just as strange. The universe may be finite in size, but unbounded, like the surface of a sphere, where you can travel forever without ever hitting a wall. The first challenge in answering this is to separate what we can see from what might exist. The observable universe is a bubble centered on us, stretching about 46 billion light years in every direction. That sounds impossibly large, yet it is not the whole story. Light has a finite speed, and the universe has a finite age. so we can only see as far as light has had time to travel. Beyond that horizon lies more universe, perhaps much more, hidden from view. The observable universe is not the limit of existence, only the limit of visibility. It is a cosmic balcony, and beyond its railing may lie an ocean we can barely imagine. Cosmologists use geometry to frame the question of whether the universe is infinite or finite. According to Einstein's theory of general relativity, space itself can curve depending on the amount of matter and energy within it. There are three broad possibilities: positive curvature, negative curvature, or flatness. If the universe has positive curvature, it is shaped something like a sphere. Travel far enough in one direction, and in theory, you could return to your starting point, just as sailors circumnavigate Earth. This would make the universe finite, but unbounded, no edge to fall off, but a total size that is not infinite. If the universe has negative curvature, it is more like a saddle, stretching outward forever. This would suggest infinite space, unrolling endlessly in all directions. Flat space, meanwhile, is the middle case, no curvature at all, extending infinitely like an endless sheet of paper. Each geometry carries its own implications, and determining which one describes reality is one of the great tasks of cosmology. Measurements of the cosmic microwave background radiation, the faint afterglow of the Big Bang, have helped shed light on this. By studying the patterns of tiny fluctuations in this ancient light, scientists can infer the curvature of space. The evidence so far points strongly toward flatness, within a small margin of error. This suggests that the universe may indeed be infinite, or at least so large that any curvature is too slight for us to detect. But the door is not fully closed on the other options. It may be finite, but unimaginably vast, so large that the curve escapes our instruments. The idea of a finite but unbounded universe can be difficult to picture because we're used to thinking of edges. Imagine the surface of Earth. It has a finite area, yet you can walk endlessly without ever finding a border. Replace two-dimensional surface with three-dimensional space, and you get the sense of a universe that loops around without walls. If you could travel in a straight line through such a cosmos, you might eventually return to where you began, though the journey would be so long that no ship or photon of light has had time to complete it. Horizon effects complicate matters further. Because the universe is expanding, distant regions are racing away from us faster than light. This does not violate relativity, since it is space itself that expands, carrying galaxies with it. But it does mean there are parts of the universe we will never see. No matter how patient we are, those regions slip permanently beyond our horizon, cut off from observation. Infinity may be hiding out there, but we will never confirm it directly. We live in a finite bubble, surrounded by the unknown. There is also the possibility of a universe with a more exotic topology. Space might wrap around in unexpected ways, like a three-dimensional version of a video game world, where leaving one side of the screen makes you reappear on the other. In such a cosmos, light from a distant galaxy could circle around and reach us from behind, creating ghostly copies of the same object in different directions. Scientists have searched for repeated patterns in the sky that might reveal such a shape. But so far, the evidence suggests our universe does not loop in this neat fashion, or at least not within scales we can currently probe. If space is truly infinite, it raises profound questions. In an endless expanse, every possible arrangement of matter could occur somewhere. Somewhere out there could be another planet identical to Earth, with another version of you listening to these words. In fact, there would not be just one, but infinitely many such copies scattered across the vastness. This is not a fanciful story, but a logical implication of infinity combined with a finite number of ways matter can arrange itself. While we may never reach those distant doppelgangers, the very thought stretches the imagination. But infinity also comes with challenges. An infinite universe would contain infinite energy, infinite galaxies, infinite stars. How do you make sense of probabilities in such a realm? If there are infinitely many versions of something, what does it mean to say one outcome is more likely than another? Physicists wrestle with these questions, and some argue that infinity should be treated cautiously, perhaps even avoided in physical theories. On the other hand, a finite universe has its own strangeness. If the universe is like a sphere, then what lies outside it? The answer is nothing in the usual sense, because space itself is the surface. Asking what lies outside is like asking what is north of the North Pole. The question dissolves as soon as you try to frame it. This is the strange beauty of a finite but unbounded cosmos. It gives you the comfort of no edges, while still sparing you the vertigo of infinity. Whichever answer is true, the universe leaves us humbled. Whether infinite or merely very, very large, it is far beyond the reach of our travels. The observable bubble is all we will ever touch directly. Yet it offers clues about the grander whole. Light from the early universe carries whispers of curvature, and the arrangement of galaxies hints at the underlying shape of space. We may never know with certainty whether infinity truly resides in the cosmos, but we can circle closer with every observation. When you stand beneath the stars, the mind naturally stretches outward. Does the universe roll on forever? Or is it a great loop folding back upon itself? The truth may never be fully within reach, but the wondering is itself a kind of journey. Infinity in space invites us to step beyond the visible and to let the imagination walk until the horizon fades, knowing that no matter how far it goes, there will always be more waiting beyond dot in the early 20th century. Most scientists believed the universe was static. The stars and galaxies were thought to hang in space like jewels pinned to velvet, shining in place, but essentially unchanging on the grandest scales. Then came a discovery that shook this picture apart. In the 1920s, an astronomer named Edwin Hubble looked closely at distant galaxies and noticed something astonishing. They were all moving away from us. Not just a few of them, not just in one direction, but nearly all of them in every direction. The farther away a galaxy was, the faster it appeared to be receding. Space itself was stretching. The universe was expanding. This realization transformed cosmology. It meant that the universe had not always been the size it is today. If everything is expanding outward now, then in the past, everything must have been closer together. Run the clock backward far enough, and you arrive at the idea of the Big Bang, a hot, dense beginning from which space and time themselves emerged. The expansion is not like an explosion throwing matter into empty space. It is space itself growing, carrying galaxies along like raisins in rising dough. Every observer, no matter where they stand, sees distant galaxies moving away because the dough is expanding everywhere at once. Hubble's discovery was only the beginning of the story. As scientists dug deeper, they found that the expansion alone could not explain the smoothness and structure of the cosmos we see. Why, for instance, is the universe so uniform in temperature across regions that could never have been in contact? To solve this puzzle, theorists proposed a bold idea: cosmic inflation. Inflation suggests that in the very first fraction of a second after the Big Bang, the universe expanded at an astonishing rate, faster than even light could cross a room. This was not galaxies flying apart, but space itself ballooning exponentially. Regions that were once close together were suddenly flung far beyond one another's horizons. The result was a cosmos smoothed out on large scales, solving the puzzle of uniformity. Inflation also stretched tiny quantum fluctuations into the seeds of galaxies, giving rise to the structures we see in the sky today. The idea of inflation grew stronger as evidence mounted. The patterns of the cosmic microwave background radiation, the ancient light still glowing from the early universe, match what inflation predicts. They show a universe that is nearly flat in geometry, and uniform in temperature, but with just the right sprinkling of irregularities to grow into stars and galaxies. Inflation may sound extravagant, but it provides a remarkably successful explanation for why the universe looks the way it does. Yet, as often happens in science, solving one mystery opened the door to new ones. Inflation, when modeled carefully, does not necessarily stop everywhere at once. Instead, it may end in some regions while continuing in others. This leads to a scenario called eternal inflation. In eternal inflation, pockets of the universe stop inflating and form bubble universes like our own, while inflation elsewhere carries on, spawning new bubbles again and again. Each bubble could have its own laws of physics, its own arrangement of matter, its own destiny. Our observable cosmos might be just one bubble in an endlessly frothing sea. This picture naturally feeds into the idea of the multiverse. If eternal inflation is correct, then infinity may lie just beyond every horizon, not as empty continuation of our own universe, but as a patchwork of countless universes. Some may be similar to ours, with stars and galaxies, while others might be utterly alien, with forces and particles arranged in unfamiliar ways. The multiverse is a radical concept, but it arises not from wishful thinking, but from the mathematics of inflationary theory. The possibility of a multiverse raises tantalizing questions. If there are infinitely many universes, do some of them contain versions of us living lives that are almost the same, but slightly different? Perhaps in one, you're watching this video with a cup of tea instead of a glass of water. In another, maybe Edwin Hubble never made his discovery, and humanity still thinks the cosmos is static. Infinity allows for every variation, every twist, every combination to play out somewhere. It is both thrilling and unsettling to consider. Of course, not all scientists embrace the multiverse idea. Some argue that because we cannot observe other universes directly, the concept risks drifting into speculation. Others counter that even if we cannot travel to other bubbles, their existence may leave subtle fingerprints, such as imprints in the cosmic microwave background. The debate is ongoing, with strong voices on both sides. What is certain is that inflation, whether eternal or not, has reshaped our understanding of how the universe began. The expansion itself has not slowed with age. In fact, it has accelerated. Observations of distant supernova in the late 20th century revealed that galaxies are not just receding. They are receding faster and faster. Some unknown energy, now called dark energy, appears to be driving this acceleration. Its nature remains mysterious, but its effect is clear. The universe will continue expanding, carrying galaxies ever further apart. Eventually, many will fade beyond our cosmic horizon, disappearing from view entirely. Our observable universe is shrinking in that sense, even as the whole expands. This paints a picture that is both lonely and inspiring. We live in a universe that is restless, stretching out in every direction. The stars we see are only a fraction of what exists, and with each passing moment, more slip beyond our sight. Infinity may not be something we can measure directly, but the expansion tells us that the cosmos is larger than anything we can hold in our imagination. Whether it is truly endless or simply enormous beyond comprehension, it dwarfs the tiny corner we inhabit. It is remarkable to think that all of this began with the careful measurement of faint smudges of light in a telescope, galaxies drifting in the night sky. From Hubble's discovery to the grand theories of inflation and multiverses, the story of expansion shows how small clues can reveal vast truths. The universe is not a still stage, but a growing dynamic structure unfolding with a momentum that seems unstoppable. Infinity may lie out there beyond every horizon, hidden in the expansion itself. Perhaps our universe is just one bubble among countless others. Or perhaps it is the single infinite stage on which all stories unfold. We may never know the full answer, but the question alone carries a quiet beauty. To live in an expanding universe is to know that there is always more beyond what we can see, an endless frontier receding into mystery. Asterisk. Black holes are the strangest objects in the cosmos, and perhaps the most perfect meeting point between the ordinary and the infinite. They begin with something as simple as gravity, the same force that holds you to the Earth and keeps the moon circling in the sky. But when enough mass collapses under its own weight, gravity goes from familiar to extreme. A star that has burned through its fuel and can no longer resist its own pull can collapse into a black hole, an object so dense that not even light can escape. Einstein's equations of general relativity describe this process with eerie precision. In the mathematics, when matter is squeezed into an ever smaller space, the curvature of space-time itself becomes more and more intense. Push the equations far enough, and they predict a singularity, a point where density is infinite, where curvature is infinite, where the very fabric of space and time breaks down. At a singularity, the laws of physics as we know them cease to function. Infinity is no longer an abstract concept, but a feature of the universe written directly into the equations. But what does this really mean? Is there truly a point of infinite density inside a black hole? Or is the singularity simply a signal that our theories have reached their limits? Many physicists lean toward the latter. General relativity is a brilliant description of gravity on large scales, but it is not a complete theory of everything. When the equations spit out infinities, it may be the universe's way of telling us we need a new framework, one that unites relativity with quantum mechanics. For now, though, singularities sit at the heart of black holes, wrapped in mystery and hidden from view by the event horizon. The event horizon is the boundary surrounding a black hole, the point of no return. Once anything crosses this threshold, whether it is a photon of light, a drifting star, or a stray astronaut, it cannot escape. From the outside, the horizon looks like a dark sphere suspended in space, an outline where light itself falls silent. Beyond it, all paths lead inward, and the singularity waits. The idea of infinity inside black holes is unsettling, but it also makes them powerful laboratories for exploring the limits of physics. They are places where gravity is so extreme that it bends light into arcs, stretches time, and pushes our understanding to the edge. Near a black hole, time itself slows down relative to an outside observer. From afar, an object falling into the horizon appears to freeze in place, stretched and dimmed. Though in its own frame, it plunges swiftly toward the center. Infinity shows up here too, not just as an abstract point, but in the perception of time, an endless pause from one perspective, a swift fall from another. Some black holes are relatively modest in size, formed from collapsed stars and measuring only a few kilometers across. Others are giants, millions or billions of times the mass of our sun, sitting at the hearts of galaxies. These supermassive black holes shape the galaxies around them, stirring stars, bending gas, and powering jets that can stretch thousands of light years. It is astonishing to think that the centers of galaxies are ruled by objects whose defining feature is a night, infinity buried within their cores. The singularity itself, however, remains out of reach. General relativity insists it is there, but quantum theory suggests the story may be different. Perhaps the singularity is not a true point of infinite density, but a region where quantum effects smear out the collapse. Some ideas, like loop quantum gravity, propose that space and time have a smallest possible scale, preventing infinities from forming. In such models, the collapse might bounce or resolve into something new. Others turn to string theory, which imagines that fundamental strings replace point-like particles, again taming infinities with structure. None of these theories are confirmed, but they highlight a deep truth. The singularity forces us to confront the unfinished business of modern physics. Even if we cannot peer into the singularity, black holes reveal themselves in other ways. They warp their surroundings, drawing in matter that spirals into their horizons. As gas falls inward, it heats up and shines brightly in X-rays, sometimes outshining entire galaxies. Black holes also merge, and when they do, they ripple the fabric of space-time, producing gravitational waves that we can now detect here on Earth. These waves carry the signature of black holes colliding, giving us direct evidence of their existence. Each detection is a reminder that infinity, whether real or symbolic, is woven into the actual universe. Philosophically, singularities challenge our sense of what is real. If infinity exists inside black holes, then nature itself contains places where our logic breaks. If instead they mark the limit of our theories, then they are signposts pointing us toward deeper laws waiting to be discovered. Either way, they occupy a unique place in science, not directly observable, yet undeniably influential. They may be hidden, but they are far from irrelevant. The thought of infinite density and curvature is daunting, but black holes also invite awe. Imagine standing at a safe distance from one, watching stars curve around its horizon like streaks of light on glass. Imagine the sense of timelessness as a falling clock seems to freeze forever at the edge. Imagine the knowledge that somewhere beyond the dark curtain, physics itself bends toward infinity. Black holes are both terrifying and beautiful, a reminder that the universe does not owe us comfort, but offers us endless wonder. There is even the possibility that black holes are not final at all. Some theories suggest they could evaporate over vast time scales, slowly releasing energy through a process called Hawking radiation. If this is true, then the singularity may not remain eternal, but may eventually vanish into the cosmos, leaving only questions in its wake. Infinity in this case would be less a permanent fixture and more a fleeting shadow, a momentary appearance in the evolution of the universe. In the end, black holes are our best glimpse into infinity made real. They are cosmic riddles wrapped in darkness, balancing on the boundary between known and unknown. Whether singularities truly exist or simply highlight the limits of our theories, they remind us that infinity is not always distant or abstract. Sometimes it waits, hidden in the hearts of galaxies, silent and immense, pulling at the edges of our understanding. Quantum physics is famous for being strange, but one of its lesser-known habits is a tendency to produce infinities at the most inconvenient times. The equations that govern the subatomic world are incredibly successful at predicting experimental results. Yet, when you look under the hood, they sometimes give answers like infinite energy or infinite probability. Clearly, the universe is not actually overflowing with infinite amounts of anything. If it were, your coffee mug would glow like a miniature sun, and the vacuum of space would collapse under the weight of boundless energy. Instead, physicists have learned that these infinities are warning clues that the mathematics is being pushed too far and needs some careful taming. One of the most notorious places where infinity appears is in the calculation of particle interactions. In quantum field theory, particles are not seen as little billiard balls, but as ripples in underlying fields. The electromagnetic field gives rise to photons. The electron field gives rise to electrons, and so on. When two particles interact, such as an electron scattering off another electron, the mathematics describes this as an exchange of virtual particles, invisible messengers, that carry the force between them. The trouble comes when you try to calculate the strength of these interactions with high precision. The formulas involve summing over contributions from virtual particles with all possible energies. And as you include higher and higher energies, the numbers spiral out of control. Left unchecked, the answer becomes infinite. Physicists faced a crisis with this problem in the early days of quantum electrodynamics. How could a theory that produced infinities ever be useful? The solution, devised in the mid-20th century, was something called renormalization. It may sound like a suspicious bit of mathematical trickery, but it works astonishingly well. The idea is that the raw numbers coming out of the equations are not the directly measurable quantities. Instead, you redefine things like mass and charge in such a way that the infinities are absorbed, leaving behind finite predictions that match experiments. The infinities have not vanished, but they have been swept into redefinitions that allow the theory to function. Richard Feynman, along with Julian Schwinger and Shinichiro Tominaga, helped pioneer this approach. Feynman once joked that renormalization was like sweeping the infinities under the rug, except that what we sweep under the rug is no longer there. However inelegant it may seem, renormalization turned quantum electrodynamics into one of the most accurate theories ever created. Its predictions match experiment to an accuracy of better than 1 part in 10 billion. Infinity had been corralled into a manageable form, like a wild horse trained just enough to pull a cart. Another arena where infinity lurks is the vacuum itself. In classical physics, a vacuum is empty, a serene nothingness. But in quantum theory, emptiness is never truly empty. The uncertainty principle ensures that even in the lowest possible energy state, fluctuations must ripple through the fields. Virtual particles wink in and out of existence, borrowing energy briefly before vanishing again. This restless activity gives rise to what is called zero-point energy, the baseline hum of the universe. The catch is that when you try to calculate the total zero-point energy of the vacuum, you end up with an infinite amount. Add up the energy of all possible modes of vibration in the quantum fields, and the sum just keeps climbing without end. Clearly, the vacuum is not infinitely energetic. If it were, the universe would have collapsed long ago. Physicists resolve this by introducing cutoff limits beyond which the calculations no longer apply, or by using renormalization once again to cancel the infinities against other quantities. Even so, the vacuum's energy remains one of the great mysteries of physics. Observations suggest that space does have small but non-zero energy in the form of what we call dark energy, which drives the accelerated expansion of the universe. But the amount we see is wildly smaller than what naive quantum calculations predict. The mismatch is not just a little off. It is off by around 120 orders of magnitude. This is sometimes called the worst prediction in physics, a sign that infinity still has the upper hand in this part of the story. Vacuum fluctuations, though invisible, can have real consequences. The Casimir effect is a striking example. Place 2 uncharged metal plates very close together, and the quantum fluctuations outside them push slightly harder than those between them, creating a measurable force that nudges the plates toward one another. This effect has been observed in laboratories and confirms that the vacuum is not truly empty. Infinity shows up here too, since the underlying calculation involves subtracting 2 infinities, the infinite energy of the vacuum in free space and the infinite energy between the plates. The difference, however, is finite and measurable, a neat trick of turning infinities into a physical effect. Quantum field theory has grown to describe not only electromagnetism, but also the weak and strong nuclear forces. Together, these form the standard model of particle physics, a framework that has passed every experimental test so far. But the price of this success is a constant battle with infinities. Each force and each particle field must be carefully renormalized. The infinities reined in, so the predictions line up with experiment. It is like maintaining a garden where weeds of infinity keep sprouting, and the mathematician's job is to prune them without destroying the flowers. There is also the hope that a deeper theory might someday make the infinities disappear altogether. Many physicists suspect that at extremely small scales, perhaps near the Planck length, space and time themselves have a discrete structure like pixels on a screen. If that is the case, then the infinities that arise from assuming continuous spacetime may evaporate, replaced by finite sums. String theory, for instance, replaces point-like particles with tiny vibrating strings, which naturally smooth out some of the infinities that plague quantum field theory. Loop quantum gravity, another approach, imagines spacetime built from discrete loops, again preventing quantities from shrinking to zero or blowing up to infinity. None of these theories are proven, but they share a common goal: to make peace with infinity by banishing it from the deepest levels of physics. It is tempting to think of infinity as a flaw bug in the equations, but it is also a guide. Each time it appears, it highlights a place where our current understanding is incomplete. Infinities in the hydrogen atom once seemed insurmountable until renormalization showed how to handle them. Infinities in the vacuum suggest there is more to learn about dark energy and the structure of spacetime. Even when they look like nonsense, infinities are telling us something important. Here be dragons, as the old maps would say. Quantum physics, then, is not just a story of tiny particles, but of infinity lurking in every calculation. From virtual particles flickering in empty space to the strange bookkeeping of renormalization, the subatomic world is filled with hints of the endless. And while the infinities themselves may not be real in any physical sense, their presence has guided some of the greatest breakthroughs in science. They remind us that infinity is not only in the farthest reaches of the cosmos, but also woven into the very fabric of the smallest scales, waiting to be tamed by human thought. Infinity does not only stretch outward toward the vastness of space, it also turns inward, burrowing into the very small. One of the oldest questions in philosophy and science is whether reality can be divided endlessly. If you take a stick and break it in half, then break one of those halves again and continue on, can this process go on forever? Or will you eventually reach a smallest possible piece, something that cannot be divided further? This is the problem of the infinitesimal, the puzzle of whether the universe is built from endlessly smaller parts, or whether nature draws a line in the sand and says, "No further." The ancient Greeks debated this intensely. The philosopher Democritus proposed that all matter was made of indivisible units he called atoms, from the word meaning uncuttable. These atoms were imagined as tiny, eternal building blocks combining to form the visible world. Meanwhile, others argued that matter was continuous and infinitely divisible. Aristotle, for example, believed that any piece of matter could always be divided again with no ultimate bottom. Both views had their appeal. Atoms offered a neat solution to Zeno's paradoxes, while infinite divisibility aligned with the smoothness of experience. You do not feel graininess when you run your hand through water. It seems seamless. For centuries, the question remained unresolved. But in the 17th century, a new mathematical tool emerged that leaned heavily on the idea of the infinitesimal. Calculus, developed independently by Isaac Newton and Gottfried Wilhelm Leibniz, allowed mathematicians to describe motion, change, and growth with stunning precision. The trick was to imagine taking steps that were infinitely small, so small they could approach zero but never quite vanish. These infinitesimals allowed you to calculate slopes of curves, areas under graphs, and the behavior of moving bodies. Without them, modern science and engineering would be impossible. At first, this idea of infinitesimal quantities was controversial. Bishop Berkeley, a critic of the early calculus, mocked them as the ghosts of departed quantities, suspicious phantoms that seemed neither zero nor finite. Over time, the rigorous machinery of limits was developed, clarifying the concept. Instead of treating infinitesimals as actual physical things, mathematicians frame them as processes. You shrink a quantity smaller and smaller, approaching a limit. In this way, calculus sidestepped the need to define a literal smallest piece of reality, focusing instead on the power of approximation. Yet the philosophical question remained: in the physical world, is there a true limit to divisibility? The discovery of atoms in the 19th century seemed to confirm Democritus's vision. Scientists realized that matter is not continuous, but composed of discrete units atoms made of protons, neutrons, and electrons. These in turn revealed deeper layers of structure. Protons and neutrons are built from quarks. Electrons, as far as we can tell, have no smaller components. The dream of a smallest possible building block seemed close at hand. But quantum physics had more surprises in store. Quantum theory revealed that particles behave like waves as well, smeared out in space and defined by probabilities rather than precise locations. The neat image of solid little marbles gave way to something stranger, more fluid. The idea of infinite divisibility resurfaced. A wave can spread continuously, but its energy comes in discrete packets, or quanta. Reality was neither entirely smooth nor entirely grainy, but something in between. Then came the Planck scale, a threshold that represents the smallest meaningful measurements of length and time. According to current physics, named after Max Planck, the founder of quantum theory, this scale is unimaginably tiny. One Planck length is about 10 to 35 meters, far smaller than the size of a proton. One Planck time is about y minus 44 seconds, a sliver of duration so brief it makes even a billionth of a second seem eternal by comparison. At scales smaller than these, our current theories of quantum mechanics and general relativity no longer make sense. The Planck scale is often described as the boundary where space-time itself may lose its smoothness and become granular pixelated, like an image zoomed in too far. Does this mean that reality bottoms out at the Planck scale? That there truly is a smallest possible length and time? Some theories say yes. Loop quantum gravity, for example, proposes that space is made of finite loops woven together, giving it a discrete structure. String theory imagines that the tiniest entities are not points, but vibrating strings with sizes on the order of the Planck length. In both cases, infinities are avoided by cutting off the endless divisibility, imposing a smallest unit. Others are more cautious. The Planck scale may not be a literal graininess, but simply the point at which our mathematics breaks down much as singularities. In black holes may signal limits of current theory rather than true infinities. If a new framework comes along, perhaps reality will turn out to be divisible even beyond the Planck scale. It is an open question whether the universe is fundamentally discrete or continuous. The implications are profound either way. If space and time are granular, then infinity is corralled in the very fabric of the cosmos. There would be no infinitely small distances, no infinitely brief moments, only the smallest units of existence. On the other hand, if reality is continuous, then infinity lurks in every crack, waiting at the bottom of every division. In such a universe, the idea of the infinitesimal is not just a mathematical convenience, but a feature of nature itself. In practice, scientists work with both ideas, depending on the problem at hand. Calculus assumes infinite divisibility and has been spectacularly successful in describing everything from planetary orbits to the flow of fluids. Quantum mechanics, meanwhile, insists on discreteness in energy levels and particle interactions, preventing infinities from running wild. Physics today is a balancing act between the infinitesimal and the finite, between smooth waves and discrete quanta. For everyday life, these debates may seem distant, yet there is something strangely comforting about them. The fact that a question as simple as, "Can I keep cutting this in half forever?" still occupies some of the greatest minds shows how deep infinity runs in our understanding. Whether the universe is ultimately pixelated or endlessly smooth, the infinitesimal has already proven to be one of the most powerful ideas in human thought. So when you picture the universe, try imagining both extremes. In one vision, reality bottoms out into indivisible grains, the atoms of space and time themselves. No smaller steps allowed. In the other, Every line can be split again, every moment subdivided forever infinity hiding in the cracks. Both possibilities are awe-inspiring, and both remind us that even in the smallest things, infinity has a way of appearing. Entropy is one of those words that often drifts into conversations as a kind of shorthand for disorder. But in physics, it has a very precise meaning. It is the measure of how many different ways a system can be arranged while still looking the same on a larger scale. A neat stack of playing cards has low entropy because there are only a few possible arrangements that fit the pattern. Shuffle them into chaos, and the entropy rises dramatically because now there are countless possible configurations. The second law of thermodynamics tells us that in a closed system, entropy never decreases overall. It may stay the same for a while, but given enough time, it will inevitably increase. This simple rule, more than almost anything else in physics, gives time its arrow. The arrow of time points forward because of entropy. When you watch a glass fall and shatter, you know instantly that the film is running in the right direction. The pieces could never spontaneously leap back into a whole glass. Even though nothing in the microscopic laws of physics forbids it, the odds are simply so staggeringly small that you can treat them as impossible. Order slips into disorder, never the reverse, and the universe keeps moving forward. But what happens if you stretch this rule out over infinite time? If entropy must always increase, does it have an ultimate ceiling? The answer is yes, and it leads to a bleak but fascinating picture known as the heat death of the universe. Over unimaginably long spans, stars will burn out, galaxies will grow dark, and energy will spread evenly across space. Entropy will reach its maximum, meaning there will be no gradients left to drive change. In such a state, nothing interesting happens. There are no differences in temperature, no flows of energy, no pockets of order from which new stars or life can arise. It is a cosmic silence, a universe that has run out of fuel, not because energy is gone, but because it is so evenly distributed that nothing can be done with it. The time scales involved are staggering. Stars like our sun will live for billions of years, but black holes will outlast them by a far greater margin. Through Hawking radiation, even the largest black holes will eventually evaporate. But this will take more than 10 to the power of 100 years. After that, the universe drifts in darkness, particles rarely meeting, space expanding ever further, entropy creeping toward its absolute maximum. In a future without end, the second law ensures that everything levels out. Infinity becomes a desert of stillness, yet infinity also creates peculiar loopholes. Over infinite time, events that are nearly impossible still have a chance to occur, because given enough waiting, the unlikely becomes inevitable. One such idea is the Boltzmann brain. Named after the physicist Ludwig Boltzmann, who explored entropy in the 19th century, this concept imagines that in the endless fluctuations of a high-entropy universe, random order might occasionally emerge. Given infinite time, particles could by chance assemble into something complex, even into a brain complete with memories of a life it never lived. These brains would briefly flicker into existence, think a thought, and dissolve back into chaos. It sounds absurd, but mathematically it is not ruled out. This leads to a philosophical puzzle. If the universe lasts forever, and Boltzmann brains arise infinitely many times, are they more common than ordinary conscious beings like us, who emerge through the long history of stars, planets, and evolution? If so, how can we trust our memories, our science, even our sense of time? Are we real observers in a vast low-entropy past, or are we temporary fluctuations in an eternal high-entropy future? Most physicists are uneasy with this conclusion, which suggests that something is missing in our understanding of entropy. Time, or cosmology. Another strange aspect of entropy over infinite time is recurrence. In a finite system, given infinite time, states will eventually repeat. Imagine shuffling a deck of cards randomly. If you shuffled forever, every possible order would eventually appear, including the perfectly stacked sequence you began with. By extension, if the universe is finite in states, but infinite in time, it could eventually cycle back to conditions nearly identical to today. The arrow of time may always point forward, but the scenery could eventually loop. Entropy also explains why the universe began in such an improbably ordered state. The Big Bang was not just hot and dense. It was extraordinarily low in entropy compared to today. This seems counterintuitive. How could the beginning of everything be less random than the present? One possibility is that gravity complicates entropy in ways that make early uniformity actually a special kind of order. Another is that our observable universe is just a small pocket within a much larger system, and we happen to emerge in a rare low-entropy bubble. Infinity offers plenty of room for such rare events, though whether that explanation satisfies is another matter. Despite the gloom of the heat death, entropy has a strange beauty. It is the quiet law that underpins evolution, memory, and history itself. Without entropy increasing, time would lose its sense of direction, and the universe would lose its story. The fact that entropy rises means stars shine, rivers flow, and life can climb from simplicity to complexity. Infinity may stretch entropy toward bleakness, but in the finite chapters we inhabit, it is the driver of everything lively and bright. Entropy's arrow also shows how tightly infinity and probability are tied together. Over everyday timescales, entropy ensures broken cups stay broken and fires burn only one way. Over infinite timescales, it allows even absurd fluctuations, from spontaneously reassembled galaxies to Boltzmann brains pondering their unlikely existence. Both the ordinary and the bizarre spring from the same rule, just stretched across different horizons of time. So the second law, often summarized as things fall apart, is not merely about decay. It is also about possibility, about the universe's tendency to explore all the configurations it can. In the short term, this gives rise to stars, life, and consciousness. In the long term, it drifts toward equilibrium, and over infinity, it opens doors to outcomes so strange they border on philosophical riddles. In contemplating entropy and infinite time, we glimpse both the fragility and resilience of order. Our moment in the universe is temporary, carved out against a tide that will eventually flatten everything. Yet within this fleeting window, complexity blooms, awareness awakens, and meaning is found. Infinity ensures that entropy will one day win, but it also ensures that improbable wonders, including our own existence, have their chance to appear. The arrow of time keeps pointing forward, and as it does, entropy writes the universe's story across infinite pages. Each moment of order is precious a spark glowing against the endless drift toward equilibrium. Perhaps the deepest beauty of entropy is that it makes every instant unique, unrepeatable, and therefore all the more meaningful, even against the backdrop of infinity. Infinity has a curious way of sneaking into equations and causing chaos. Mathematicians may treat it as a useful abstraction, but in physics, infinity often spells disaster. When a formula spits out an infinite energy or an infinite value for some measurable property, it usually means the theory has been stretched past its limits. Nature, as far as we can tell, does not actually deal in infinite energy. If it did, we would be living in a very different universe, one where every light bulb blazed like a star and perpetual. Motion machines were not just dreamt up in notebooks, but humming in kitchens everywhere. To understand why infinity is so disruptive, consider the conservation of energy. This principle, one of the bedrocks of physics, tells us that energy cannot be created or destroyed, only transformed. The total energy of a closed system stays constant. Drop a ball, and its potential energy becomes kinetic. Rub your hands together, and motion becomes heat. The ledger always balances. But introduce infinity and the ledger collapses. An infinite amount of energy has no balance point. It cannot be accounted for within a finite system. It is like trying to fit the ocean into a teacup. The mathematics floods over the edges and the physical meaning evaporates. Perpetual motion is one of the most persistent dreams born from the allure of infinite energy. For centuries, inventors tried to design machines that would run forever without fuel, drawing energy from nothing or producing more than they consumed. Wheels with hidden weights, magnets arranged in endless cycles, contraptions meant to turn their own motion into eternal power. All have been sketched, built, and inevitably debunked. The problem is not lack of ingenuity, but the laws of thermodynamics. The first law, conservation of energy, forbids energy from appearing out of nowhere. The second law, the rise of entropy, ensures that some energy is always lost as heat, gradually dissipating and rendering perfect efficiency impossible. A perpetual motion machine is not just impractical. It is fundamentally forbidden by the very framework of physics. Quantum theory, with its strange fluctuations and zero-point energy, sometimes tempts people into thinking that loopholes might exist. After all, the vacuum itself is not truly empty. Particles flicker into and out of existence. Energy fluctuates restlessly. Could this be tapped as a source of infinite power? The short answer is no. These fluctuations cannot be harvested like fuel, because doing so would require more energy than you gain. They are background jitters, not a free lunch. The universe remains stingy with its energy, doling it out according to strict rules that never allow infinity to take hold in practice. Still, infinities appear regularly in calculations. In quantum field theory, as mentioned before, integrating over all possible particle energies produces infinite results. Left alone, these infinities suggest infinite energy densities, which are physically absurd. Renormalization was developed to manage this redefining quantities so that the infinities cancel out and predictions remain finite. While it works, it also highlights how fragile our models are. Infinity is a reminder that equations are only approximations, maps that sometimes stretch too far from the terrain. Another notorious example comes from classical physics itself, the problem of the electron. In early models, the electron was treated as a point particle with electric charge concentrated at a single point. The electric field of such a particle becomes infinitely strong as you approach it, implying infinite self-energy. Clearly, electrons do not sit around with infinite energy bubbling inside them, or the universe would not function. The infinity here is not real, but a symptom of the model's incompleteness. Quantum mechanics later softened the picture, spreading out the electron into a probability cloud rather than a strict point. Even so, questions about self-energy still arise and remain a playground for physicists seeking deeper theories. Infinite energy also appears when physicists try to describe the early universe. At the singularity of the Big Bang, general relativity predicts infinite density and infinite temperature. These infinities are not physical entities, but signs that the theory breaks down at extreme conditions. They tell us that new physics, perhaps quantum gravity, is required to describe what really happened at the beginning. Infinities in this sense are not answers, but alarms ringing loudly to announce the limits of our understanding. It is worth pausing to consider what the world would be like if infinite energy were possible. Imagine a kettle that boiled forever without a plug, or a car that ran without fuel, its tank endlessly refilling. It sounds delightful until you realize that infinite energy would make the universe completely unstable. Any tiny fluctuation could unleash boundless amounts of power, overwhelming everything. Stars, planets, and life itself would not exist in such chaos. The impossibility of infinite energy is not an arbitrary rule. It is a safeguard that allows stable structures, complexity, and life to emerge. There are, however, clever ways to mimic perpetual motion in limited domains. Superconductors, for instance, can carry electric currents with zero resistance. Once a current is established, it can flow for years without additional energy input. This may look like a perpetual motion machine, but it is not truly one. The system still requires careful conditions, such as very low temperatures, and it does not create energy. It simply preserves it unusually well. Similarly, quantum systems can linger in metastable states that appear long-lived. But again, no new energy is generated. These examples remind us that while physics allows fascinating tricks, the fundamental rules remain unbroken. The dream of infinite energy often resurfaces in discussions of cosmology. Dark energy, the mysterious force accelerating the expansion of the universe, sometimes inspires speculation about endless power sources. Yet, dark energy is not something we can bottle or burn. It is a property of space itself, uniform and untappable. Even if it carries energy, it does not break the conservation laws within our observable bubble. Infinity, once again, is kept in check. In the end, infinity is less like a treasure chest of energy and more like a cautionary mirage. Each time it appears in physics, it is a signal that the equations have stepped beyond their domain. It is not nature that is infinite, but our models straining against their boundaries. Perpetual motion machines remain in the realm of fantasy, not because engineers lack creativity, but because the universe has rules that even clever gears and magnets cannot defy. Infinity breaks physics not because the cosmos dislikes big numbers, but because real energy must always balance, flow, and transform. When infinities appear, they reveal gaps in our understanding or shortcuts in our models. They remind us that the universe is subtle, neither giving away energy for free nor hoarding it without limit. Energy is conserved, transformed, and sometimes hidden, but never infinite in any physical sense. So the infinite energy question is less about building impossible machines and more about listening to what physics is telling us. Infinity is the point where equations whisper, "Look deeper." It is a reminder that our most powerful theories are still provisional, still incomplete. And it is a comfort, too, that the laws which forbid infinite energy are the same laws that allow stars to shine steadily, galaxies to hold together, and a fragile world like ours to exist in balance. The universe had a beginning, or at least that is what most evidence suggests. The Big Bang Theory, supported by cosmic background radiation and the expansion of galaxies, tells us that space and time once sprang from a hot, dense state nearly 14 billion years ago. If the cosmos had a beginning, it is natural to ask, will it also have an end? This question has fascinated scientists, philosophers, and storytellers alike. And once again, infinity lurks in the answers. The possible endings of the universe are painted in shades of endless time, infinite density, and infinite expansion. One vision of the cosmic finale is the Big Crunch. Imagine that gravity, the same force pulling your feet to the floor, is strong enough to halt the expansion of the universe and reverse it. Galaxies would slow, then stop, then begin to rush back together. The sky would grow brighter with crowded stars as everything collapses inward. Eventually, the entire universe would shrink into a state of extraordinary density and heat, much like its beginning. At the final moment, densities and temperatures would soar toward infinity. The Big Crunch is a universe folding itself back into a point, a mirror image of the Big Bang. This ending, while dramatic, does not currently appear to be the likeliest. Observations of distant galaxies show that expansion is accelerating, driven by dark energy. If this continues, the universe will not collapse, but expand forever. Still, the Big Crunch holds a certain poetic balance. An infinite density at the end mirrors the infinite density at the beginning, a cosmic symmetry of birth and death. Some theories even imagine that such a collapse could trigger a new Big Bang, creating a cycle of universes rising and falling endlessly. If that were the case, time itself might loop, with infinities of beginnings and endings stitched together in a grand cosmic heartbeat. A different fate is the heat-death of the universe. Here expansion continues, but instead of collapsing, everything drifts further apart. Stars burn out. Galaxies thin and black holes slowly evaporate through Hawking radiation. Entropy, the measure of disorder, creeps ever closer to its maximum. Over an infinite span of time, energy spreads so evenly that no work can be done. The cosmos becomes a dark, cold ocean where nothing new can form. It is not a sudden, traumatic ending, but a slow fade into silence stretched across infinity. The time scales of heat death are so vast that they strain the imagination. Long after the last stars exhaust their fuel, brown dwarfs, the cold remnants of stars like our sun, will remain. After even longer periods, protons themselves may decay, leaving only radiation and faint particles drifting through ever-expanding space. Eventually, even black holes will vanish, releasing their energy in a whisper of radiation. What is left is a universe approaching infinite uniformity, a stillness where entropy has reached its maximum and time itself loses meaning. The heat, death is infinity, not as a violent event, but as an endless waiting, an infinite future in which change has no foothold. The Big Rip offers a third possibility, and it is perhaps the most unsettling. In this scenario, dark energy does not merely drive expansion, but grows stronger over time. Galaxies rush away faster and faster until their bonds cannot hold. Stars are pulled from galaxies. Planets are torn from stars, and eventually atoms themselves are ripped apart. As the expansion accelerates without limit, the scale factor of the universe heads toward infinity in a finite time. In other words, the universe does not drift quietly into darkness, but ends with a catastrophic tearing, where even the fabric of space-time is stretched beyond endurance. The Big Rip would not only destroy structures, but also mark a kind of infinity of expansion. Distances grow faster than light can bridge, and eventually, all points of the universe are isolated. Each particle becomes a lonely island before even those dissolve. Unlike the heat death, which plays out across an infinite future, the Big Rip happens on a specific schedule. Depending on the properties of dark energy, it could occur in tens of billions of years, or never at all. The uncertainty adds to the tension. The cosmos may drift forever, collapse into fire, or tear itself apart. These three endings illustrate how infinity hides in different guises. A big crunch presents infinity in density, where everything is crushed into a singular point. The heat death presents infinity in time, where the universe fades, not in fire, but in an endless stretch of stillness. The Big Rip presents infinity in expansion, where distances grow without limit until the universe itself unravels. Each possibility is bound to infinity in one form or another, as though the cosmos cannot conclude without brushing against the endless. It is worth noting that these scenarios are not the only ideas on the table. Some physicists explore bouncing cosmologies, where the universe expands and contracts in cycles without end. Others consider quantum fluctuations at the end of heat, death, where rare events like Boltzmann brains or even new universes might arise spontaneously. Infinity, once again, ensures that even the most unlikely events eventually occur. In such views, the end is not truly an end, but a transition, with new beginnings arising from infinite time. What unites all of these speculations is the recognition that infinity is both a tool and a warning. When equations predict infinite density, as in the Big Crunch, it is a signal that our theories are incomplete. When entropy stretches into infinite time, it suggests the limits of human imagination more than a definitive picture. When expansion accelerates toward infinite growth, it challenges our assumptions about the stability of cosmic laws. Infinity is not just a number, but a horizon that physics brushes against when exploring the extremes. For human beings, These cosmic endings are both terrifying and strangely calming. Terrifying because they remind us of the fragility of everything we know, but calming because they are so distant that they feel more like stories than threats. The heat death will not trouble anyone alive today, nor their descendants for countless generations. The Big Rip, if it ever comes, lies billions of years ahead. The Big Crunch, if it is real, would take even longer. Infinity as a way of softening, fear with sheer scale, placing our lives in perspective against the endlessness of cosmic time. So, how will the universe end? The truth is that we do not know. Each theory carries its own infinities, its own flavor of the endless. Perhaps the cosmos will collapse. Perhaps it will drift forever. Or perhaps it will tear itself apart. Or perhaps there is an ending we have not yet imagined, waiting quietly beyond the reach of our current theories. What is certain is that infinity will be there in some form, shaping the finale of the grandest story we know. Whether as density, time, or expansion, the universe seems destined to end by embracing the infinite. Infinity often inspires one of the most provocative questions in science and philosophy. If the universe is infinite, does that mean every possible event happens somewhere? Does infinity guarantee that there are endless versions of you living out endless variations of your life across a vast cosmic patchwork? This is the allure of the multiverse, an idea that stretches the imagination as far as the observable universe and then keeps going. The multiverse is not a single theory, but a family of possibilities. One of the simplest comes directly from the notion of infinite space. If space truly stretches on without bound, then matter must be arranged in countless different ways. Because there are only a finite number of ways atoms can combine within a given region, those arrangements must eventually repeat. In an infinite cosmos, there could be regions unimaginably far away that look exactly like ours, right down to another Earth, and another, you sitting in a room listening to this story. The odds of this happening locally are tiny, but stretched across infinity, the improbable becomes inevitable. Another pathway to the multiverse comes from cosmology and the idea of eternal inflation. Inflation, the rapid ballooning of space in the first instant after the Big Bang, explains many of the large-scale features of the universe. But in many models, inflation never stops entirely. Instead, it ends in some regions, producing bubble universes like ours while continuing elsewhere. Each bubble can have its own physics, its own constants of nature, perhaps even its own number of dimensions. The result is a cosmic froth of universes, each one unique. Infinity here is not just repetition of the same, but variation without limit. Quantum mechanics adds its own twist with the many worlds interpretation. In this view, every time a quantum event has multiple possible outcomes, the universe branches. One version of you sees the coin land heads. Another sees tails. The superposition of states never collapses. Instead, reality splits, generating an infinity of parallel histories. Whether or not this interpretation is correct is hotly debated, but it demonstrates how infinity can creep into the very structure of possibility itself. The philosophical consequences of these ideas are enormous. If there are infinitely many universes, then every possible history is played out somewhere. There is a universe where the dinosaurs never went extinct. Another where humanity never evolved. Another where you made a different choice on an ordinary morning and set your life on a new path. There may even be universes where the laws of physics differ so radically that life takes forms we cannot even imagine. Infinity in this context does not just mean endless copies, but endless creativity, a boundless canvas of realities. But does infinity truly guarantee everything? The answer depends on the kind of infinity we're dealing with. If space is infinite, but governed everywhere by the same physical laws, then only the possibilities allowed by those laws will occur. You may find endless Earths, But you will not find a universe where 2 plus 2 equals 5. If the multiverse includes different laws, then the scope of possibilities grows enormously, perhaps to the point where nearly anything conceivable could exist somewhere. Still, not every story the imagination spins is physically meaningful. Infinity opens many doors, but not all of them. One common objection to the multiverse is that it may be untestable. If other universes exist but are forever beyond our reach, how can we ever know? Some physicists argue that the multiverse is more of a philosophical idea than a scientific one, since science depends on observation and falsifiability. Others counter that even if we cannot see other universes directly, their existence may leave indirect signatures. For example, if our bubble universe collided with another during inflation, it might leave subtle patterns in the cosmic microwave background. The search for such evidence is ongoing. Even without experimental proof, the multiverse has a certain explanatory power. One puzzle in physics is why the constants of nature seem so finely tuned for life. The strength of gravity, the charge of the electron, the expansion rate of the universe's small changes in these values would make life, as we know it, impossible. If there is only one universe, this fine-tuning is a remarkable coincidence. But if there are infinitely many universes, each with different constants, then it is not surprising that we find ourselves in one of the rare life-friendly pockets. It is simply a selection effect. Life arises where conditions allow it, and observers will naturally find themselves in such a universe. Infinity, however, does not come without paradox. If there are infinitely many universes, how do we assign probabilities? How do we say one outcome is more likely than another when both occur infinitely often? This measure problem haunts discussions of the multiverse. In an infinite landscape, almost everything that can happen will happen infinitely many times. Distinguishing meaningful predictions from noise becomes a subtle art. Infinity makes possibility boundless but also slippery. For all the debates, the idea of parallel worlds remains one of the most captivating consequences of infinity. It has long inspired stories and myths, from ancient speculation about countless worlds to modern science fiction tales of alternate histories. The difference today is that these ideas are not just fantasies, but live possibilities emerging from serious physics. Inflation, quantum mechanics, and cosmology all whisper hints that reality may be broader than what we see. There is also a deeply human element to the fascination with parallel worlds. Who has not wondered what life would be like if they had made a different choice, taken another path, or been born into a different time? The multiverse, whether real or not, offers a stage for those questions to play out on an infinite scale. Somewhere, perhaps, there is another version of you living that alternative life. Somewhere, perhaps, another version of humanity made it through challenges differently and built a world unlike ours. The multiverse reflects our longing to imagine beyond the single thread of history we inhabit. At the same time, it reminds us that the thread we do inhabit is unique. Even if countless variations exist, this moment, this particular unfolding, is ours. Infinity does not diminish it, but highlights its preciousness. Whether or not other worlds exist, the fact that we can conceive of them shows the power of imagination sparked by the idea of the endless. In the end, the multiverse may remain unproven, a vast speculation forever beyond confirmation. Or it may turn out to be real, with evidence waiting quietly in the patterns of ancient light or the mathematics of future theories. Either way, the notion of parallel worlds embodies the essence of infinity, the sense that reality is larger than any one version, any one history, any one possibility. Infinity may not guarantee that everything happens, but it guarantees that wonder will never run out. Infinity is everywhere in human thought, yet it never quite fits comfortably in the mind. We can say the word easily enough, write down the sideways figure 8 symbol, or describe something as going on forever. But when pressed to picture infinity, the imagination falters. The brain is built for finiteness, for counting steps, for remembering days, for recognizing patterns in things that begin and end. To grasp what never ends is to stretch beyond the architecture of our neurons. And yet, again and again, humanity has reached for infinity, using mathematics, metaphor, and imagination as tools to bridge the gap. Children encounter infinity early, usually in the form of counting games. A child might proudly announce they can count to the biggest number, only to be told that no matter how high they go, there is always one more. This discovery is both thrilling and unsettling. Numbers never stop. Many children then invent the idea of infinity as the ultimate trump card, the largest possible number. Of course, mathematicians later explained that infinity is not a number at all, but a concept something outside the usual rules. Still, the instinct to imagine infinity as a kind of unreachable peak is a natural attempt to contain the uncontainable. The adult mind does not escape this tension. Even trained mathematicians acknowledge that infinity is an abstract tool rather than a tangible quantity. The idea of multiple infinities, as discovered by Georg Cantor, challenges intuition even further. It is difficult enough to imagine endlessness, but the notion that there are infinities larger than other infinities stretches logic to the breaking point. Cantor himself once described his work on transfinite numbers as walking along a strange landscape where familiar landmarks had vanished. For most of us, the mind copes with such concepts not by fully picturing them, but by learning rules for how they behave in mathematics. We handle infinity symbolically, with careful steps, without ever truly seeing it. Psychologists who study numerical cognition find that the human brain is tuned for magnitude, but not for infinity. People can quickly estimate quantities up to a certain size, and with training, they can manage very large numbers. But at some point, the difference between 10 trillion and 100 trillion becomes meaningless to intuition. Infinity, being larger than any number, lies permanently outside this zone. To think about it, we rely on metaphor, the endless road, the unbroken horizon, the boundless ocean. These images help carry the weight of the idea, even though they remain finite in reality. Religions and philosophies have long used such metaphors to approach infinity. The eternal, the divine, the infinite mind of God. These are ways of placing the concept into a frame humans can feel, if not fully comprehend. To call something infinite is to grant it a quality of ultimate otherness, a scope that escapes human limitation. Whether in theology, poetry, or art, infinity becomes a symbol of transcendence. In these contexts, the infinite is not something to calculate, but something to contemplate. Mathematics, however, provides a more disciplined bridge. The invention of calculus showed how infinities can be tamed into practical tools. By working with limits, mathematicians found a way to make sense of processes that go on without end. The infinite sum of fractions can converge to a finite result. An infinitely small slice of time can be used to calculate velocity. The brain does not need to picture infinity directly. It only needs to manipulate it through logic and symbol. This symbolic handling of infinity has allowed humans to build bridges, send spacecraft across the solar system, and design the electronics that fill our lives. Infinity, though never seen, is everywhere in the mathematics of modern life. Imagination also plays its part. Writers and philosophers have delighted in playing with infinity as a concept that tests the boundaries of understanding. Jorge Luis Borges famously wrote stories about infinite libraries and endless books thought experiments that turn infinity into something tangible enough to haunt the mind. Douglas Hofstadter, in his work on self-reference and consciousness, explored infinity through recursive patterns loops that fold back on themselves, hinting at endless descent. These imaginative exercises do not solve infinity, but they keep it alive in the cultural imagination. showing how the human mind circles around it in art, as well as in science. There is even a curious relationship between infinity and human memory. While no one can actually recall infinite experiences, the mind has a habit of compressing and extending. A single moment can feel endless, such as waiting in silence, while entire years can vanish in a flash of recollection. The brain, in this sense, produces its own illusions of infinity, stretches of experience that feel timeless, or loops of thought that spiral endlessly inward. This subjective infinity is not mathematical, but psychological. Another way the mind brushes against the boundless. Philosophers have long argued about whether the mind can ever truly grasp infinity. Immanuel Kant suggested that the concept of infinity is an idea of reason rather than an intuition of the senses. We cannot perceive infinity directly, but we can think it, frame it, and reason about it. This aligns with how people actually use infinity, never seen, never touched, but manipulated through language and thought. Infinity becomes a mirror for the mind itself, always reaching beyond its limits. Interestingly, neuroscience reveals that the brain seems to use different circuits when dealing with very large numbers compared to small ones. There are regions in the parietal lobe that light up when we estimate magnitudes, and these same regions may be stretched when we contemplate concepts like endlessness. Infinity does not live in a single part of the brain, but emerges from the collaboration of networks that handle numbers, imagination, and metaphor. In a sense, thinking about infinity is like building a bridge out of multiple mental tools lashed together, each one too weak on its own, but powerful in combination. This raises another question. Do we need to fully understand infinity to make use of it? The answer seems to be no. Humanity has built mathematics and physics that rely deeply on infinity. Yet no individual truly comprehends it in all its strangeness. This is not unusual. We also use quantum mechanics, even though no one fully understands it in the intuitive sense. The mind manages by working with symbols and rules, by pushing imagination just far enough to get results. Infinity, then, is less something we hold in the mind and more something we orbit circling it with mathematics, stories, and metaphors. Infinity also highlights the unique power of imagination to stretch beyond survival needs. Our ancestors did not need infinity to hunt, gather, or farm. Yet somewhere along the way, humans began to ponder the endless, the stars without count, the days without end, the numbers that keep rising. Infinity reveals the restlessness of the mind, its refusal to stop at the visible and measurable. Even if we cannot comprehend it fully, we continue to reach for it. Perhaps that is the deepest truth about the infinite mind. We may never truly picture infinity, but in striving to, we uncover the creativity and flexibility of our own thought. Mathematics turns the endless into a tool. Metaphor makes it vivid. Imagination makes it playful. The brain wrestles with infinity, not to conquer it, but to learn from the struggle. Each failed attempt to grasp it directly leaves behind new insights, new art, new discoveries. Infinity, in the end, is not just out there in numbers or in the cosmos. It is inside us, in the way our thoughts expand beyond limits, in the way we can imagine what we cannot see, in the way we can write symbols that gesture toward the endless. The human mind cannot hold infinity completely, but it can dance with it, and that dance is one of the most remarkable things our species has ever achieved. Infinity is one of those ideas that, instead of answering questions, often leaves us with more. Each time we think we've captured it, it slips between our fingers, leaving behind riddles and paradoxes. In this sense, infinity is less a solution and more a puzzle maker. From ancient philosophy to modern cosmology, it creates scenarios that bend reason, confound intuition, and challenge even the most patient thinker. The paradoxes of infinity are not just quirks of mathematics or philosophy. They reveal deep tensions in how we try to make sense of the endless. One of the earliest and most famous explorers of infinity's riddles was Zeno of Elea, who lived in Greece during the 5th century before the Common Era. His paradoxes remain classics in the study of infinity precisely because they use simple logic to produce deeply unsettling conclusions. Take his dichotomy paradox. To walk across a room, Zeno pointed out, you must first get halfway. Before reaching the halfway point, you must cover half of that distance, and before that, half again. This sequence of halves continues endlessly. If you must complete an infinite number of steps to cross the room, how do you ever arrive at the other side? The Achilles and the tortoise paradox presses the point even further. Imagine Achilles, the fastest of heroes, racing against a tortoise with a small head start. Zeno argued that Achilles can never pass the tortoise because by the time Achilles reaches the spot where the tortoise was, the tortoise has moved a little ahead. Each time Achilles catches up to where the tortoise was, the tortoise has already advanced again. This repeats infinitely, so Achilles never quite overtakes the slow creature. Of course, in reality, Achilles would speed past quickly. But Zeno's paradox highlights the strange conflict between infinite divisibility and our intuitive sense of motion. The paradoxes are not meant to prove motion impossible, but to reveal how infinity complicates even the simplest actions. Mathematics eventually resolved these puzzles through the concept of convergent series. When you add 1/2 plus 1/4 plus 1/8 and so on, the infinite series does not spiral out forever, but approaches a finite number, in this case, 1. Achilles can pass the tortoise because the infinite sequence of steps takes only a finite time. Yet, even with the resolution, Zeno's paradoxes continue to unsettle, reminding us that infinity is never far from the ordinary act of walking across a room. Centuries later, infinity revealed another paradox through Hilbert's Hotel of Thought experiment, imagined by the mathematician David Hilbert. This hotel has infinitely many rooms, all occupied. At first glance, you might think it is full, with no space for new guests. But infinity has other ideas. If one more guest arrives, the manager can simply move the person in room 1 to room 2, the person in room 2 to room 3, and so on down the line. Now, room 1 is free and everyone still has a bed. If an infinite bus of new guests arrives, the manager can move each current guest from room N to room 2N, doubling all room numbers and freeing all the odd-numbered rooms. Suddenly, there is space for infinitely many more. Despite the hotel already being full, Hilbert's hotel reveals how infinity refuses to obey the ordinary logic of numbers. A set can be complete and still have room for more. Subtract infinitely many occupants, and you may still be left with infinitely many. Infinity is elastic, expanding, or contracting without ever settling into the familiar arithmetic of the finite. These paradoxes are not errors in reasoning, but reflections of how infinity truly behaves in mathematics. They challenge our sense of scale and fairness. How can full also mean room for more? Philosophy, too, has long wrestled with infinite regress, a paradoxical loop of explanations with no starting point. If every effect requires a cause, then every cause must also have a cause. This leads backward forever, with no first cause to anchor the chain. Aristotle struggled with this, as did medieval theologians. Theologians solved it by positing an uncaused cause, often identified as God. Philosophers, however, have never fully escaped the puzzle. Infinite regress arises in arguments about knowledge as well. If every belief must be justified by another belief, and each justification requires its own, then the chain extends without end. Do we eventually ground knowledge on self-evident truths, or do we wander endlessly through justification after justification? Infinity in this form becomes a trappist staircase without a bottom step. Cosmology inherits its own share of paradoxes tied to infinity. Consider the idea of an eternal past. If the universe had no beginning, then an infinite amount of time has already passed. But if an infinite past has already unfolded, how could we ever arrive at the present? It would be like trying to climb up a ladder with infinitely many rungs below you. No matter how much progress you make, the top always remains infinitely far away. This paradox pushes many cosmologists toward the idea that the universe had a definite beginning, such as the Big Bang, rather than an infinite past. Another cosmological riddle comes from the concept of an infinite universe filled with stars. If stars were evenly distributed in an infinite cosmos, then no matter which direction you looked, your line of sight would eventually land on a star. The night sky should blaze with unbroken light. This paradox, known as Olber's paradox, troubled astronomers for centuries. Its resolution lies in the finite age of stars and the expansion of the universe. Distant starlight has not had time to reach us, and galaxies are receding, stretching their light into invisibility. Yet the paradox remains a sharp reminder that infinity is not just an abstract idea, but something that must be reconciled with observation. Even probability theory feels infinity's sting. If you flip a fair coin infinitely many times, every possible sequence of heads and tails must appear somewhere. There will be stretches of 1,000 heads in a row, stretches of perfect alternation, and every pattern imaginable. Infinity ensures that certainty and randomness blur. The coin flip paradox mirrors the unsettling idea of the multiverse. Given infinite trials, everything permitted by the rules will happen, no matter how absurd it seems. These paradoxes show that infinity is not gentle or polite. It is disruptive, bending reason and defying intuition. Yet paradoxes are also productive. They force us to refine our mathematics, sharpen our logic, and reconsider our assumptions. Zeno's puzzles helped inspire calculus. Hilgert's hotel clarified the nature of infinite sets. Infinite regress pushed philosophy toward deeper reflections on causation and knowledge. Infinity's riddles, though confounding, have driven progress as much as confusion. It may be that paradox is the natural language of infinity. When we step into the endless, we leave behind the rules of the finite. Our concepts of full and empty, near and far, cause and effect all buckle under the weight of the infinite. Infinity creates riddles not because it is broken, but because our tools are finite. The human mind works in terms of beginnings and endings, yet infinity offers neither. It is a mirror reflecting the limits of thought, always giving back questions where we expected answers. Infinity as paradox is not just a nuisance. It is also a source of wonder. To confront these riddles is to glimpse the strangeness of the universe and the boundaries of understanding. Perhaps the point is not to solve every paradox, but to appreciate the way infinity forces us to think differently. In the endless, certainty is rare, but imagination thrives. The riddles of infinity are not doors to be shut, but windows to be opened, letting in the strange, unsettling, and beautiful light of the infinite. Physicists have an uneasy relationship with infinity. Mathematicians can embrace it, play with it, and build entire frameworks around it. But in physics, infinities usually mean trouble. They creep into equations like unwelcome guests. And when they do, it is often a signal that the theory has reached its breaking point. In the physical world, nothing we know of is truly infinite. Energies, densities, curvatures, whenever these appear as infinite in the mathematics, it is less a revelation about reality and more a warning that our description has gone off the rails. One of the clearest examples comes from Einstein's general relativity. The theory beautifully describes how matter and energy shape space-time, producing gravity not as a force but as curvature. It predicts orbits, explains the bending of light around stars, and even anticipates the expansion of the universe. Yet hidden in its equations are singularities, places where density and curvature become infinite. At the center of a black hole, for instance, the equations insist that matter collapses into a point of infinite density. At the very beginning of the cosmos, the Big Bang appears as a singularity of infinite temperature and density. These infinities are not triumphs of the theory, but its failings. They mark places where general relativity, despite all its successes, cannot be the whole story. Quantum field theory runs into its own infinity problem. When calculating the interactions of particles, the equations tend to blow up. For example, the self-energy of an electron, the contribution of its own electric field to its mass, comes out infinite if treated naively. Left alone, the predictions would make no sense. Physicists devised the method of renormalization to manage these infinities, redefining quantities so the theory gives finite, accurate results. The procedure works astonishingly well. Quantum electrodynamics, after renormalization, matches experiments to an accuracy of better than 1 part in 10 billion. But many physicists still find this suspicious a bit, like sweeping dust under the rug. The theory works, but the presence of infinity suggests it may be a patch rather than a final description of reality. The real clash comes when general relativity and quantum mechanics meet in quantum gravity. Both theories are brilliant on their own. Relativity governs the large-scale structure of the universe, while quantum mechanics rules the tiny scales of atoms and particles. But when you try to combine them, infinities explode across the equations. A quantum version of gravity, treated with the same techniques as other forces, becomes non-renormalizable. The infinities cannot be neatly absorbed into redefinitions. They spiral out uncontrollably. This is why black hole singularities and the Big Bang are so troublesome. They are arenas where both gravity and quantum effects are strong, and where our current theories fail spectacularly. Cosmology adds further layers to the discomfort. If the universe is infinite in space, then it contains infinite matter and infinite energy. This creates problems for probability. How do you say something is likely when both the event and its alternatives happen infinitely many times? In eternal inflation models, where new universes bubble into existence endlessly, this problem becomes acute. Physicists call it the measure problem. How do you measure likelihoods in an infinite set? Without a solution, predictions lose their meaning. Infinity, in this sense, makes probability dissolve into ambiguity. Physicists distrust infinities, not because they dislike big numbers, but because infinity in an equation usually means the theory has left the realm of testable reality. Infinity signals that the framework has been stretched beyond where it applies. It is like a map that works beautifully in the city, but when extended into the ocean, fills with nonsense and contradictions. The task then is not to accept infinity as literal, but to search for a deeper theory where the infinities disappear. Several candidates aim to resolve this. String theory is one approach. By replacing point-like particles with tiny vibrating strings, it softens the infinities that arise when interactions are pushed to very small scales. Strings smear out what would otherwise be singular points, preventing densities from becoming infinite. In this way, string theory offers a graceful way to avoid the catastrophic breakdowns of point-based physics. Another approach, loop quantum gravity, imagines space-time itself as woven from discrete loops. Instead of being infinitely divisible, space and time have a smallest possible unit, the Planck scale. This granularity prevents quantities like curvature from blowing up into infinity, replacing singularities with finite, calculable structures. Even without a full theory of quantum gravity, there are hints that infinities may vanish once the right framework is found. Some models of black holes suggest that the singularity is replaced by a finite region where quantum effects create a kind of bounce, avoiding infinite density. Similarly, the singularity at the Big Bang might not be the beginning of everything, but a transition from an earlier state, with quantum laws smoothing out what relativity renders infinite. Infinities also raise practical questions about what is real versus what is artifact. The infinite energy of the vacuum, predicted by quantum field theory, for example, is clearly not physically manifest in daily life. The mismatch between the predicted vacuum energy and the observed value of dark energy, sometimes called the cosmological constant problem, remains one of the great puzzles of physics. The discrepancy is so large, it suggests that our use of infinity in these calculations is deeply flawed, a signal that a revolution in understanding is needed. There is another reason physicists distrust infinity. It erodes explanatory power. If a theory allows infinity freely, almost anything can be justified. Predictions lose precision and falsifiability fades. Theories become less about describing the world and more about hiding behind the endless. To keep science meaningful, infinity must be treated with suspicion, constrained or eliminated whenever it appears. Yet there is also humility in this. Infinity is a teacher, pointing out where knowledge fails. Each time it appears, it marks a place where our best theories collide with the unknown. Black holes, the Big Bang, the structure of space-time, these are all arenas where infinity whispers. Look deeper. Far from being useless, infinities are guiding lights, showing the boundaries of our understanding. The search for a deeper theory is in many ways a search for a universe without infinities, or at least one where they are understood rather than feared. Whether the answer lies in strings, loops, or some entirely new framework, the goal is the same: to make sense of reality in a way that does not collapse into the endless. Until then, physicists will continue to treat infinities with suspicion, wary of their ability to break the rules of the game. Infinity, after all, is not a number you can measure or a state you can observe. It is a horizon of thought, a boundary that appears when our finite minds and equations try to grasp the whole of reality. When it breaks physics, it is not the universe failing us, but our models revealing their limits. And in those cracks, illuminated by the glare of infinity, new theories are waiting to be born. Infinity is a word that carries two faces. One face is unsettling, a reminder of limits we cannot overcome, of equations that collapse into nonsense, of futures that stretch into cold silence. The other face is comforting, a vision of continuity, of endlessness that softens the fear of endings. It is both abyss and embrace, mystery and reassurance. As humans, finite beings with short lives and fragile frames, we can feel both awe and unease when looking at the endless. Yet, it is precisely this tension that gives infinity its beauty. When we think of infinity, we often imagine it as overwhelming. The idea that numbers never end, that space might stretch forever, or that time could flow without a final stop can make the mind reel. Standing beneath a night sky already hints at this unease. The stars seem countless, and beyond them lie more galaxies, more horizons, more stretches of the unknown. To picture it all without limit is to feel small in a way that is almost dizzying. Some people find this frightening, a sense of being lost in something too vast to comprehend. But the same idea can also soothe. Infinity means there is no final law, no ultimate boundary at which everything stops. For those uneasy about endings, infinity offers a kind of assurance. The story does not simply close, but continues. Time without end may be daunting, but it's also gentle in its promise of continuity. Just as the ocean does not halt at the horizon, but keeps flowing beyond our sight, infinity reminds us that reality, whatever it may be, is larger than our fears. Mathematics shows infinity in playful ways. Hilbert's Hotel welcomes infinite guests with ease. Calculus turns infinite sums into precise results. Even in paradox, infinity reveals elegance. The idea that an infinite series can equal a simple number, or that endless divisions can add up to a finite distance. These tricks highlight infinity, not as a monster, but as a hidden order, a logic that makes the impossible manageable. The fact that such strangeness can be made useful in describing real-world bridges, orbits, and circuits shows how beauty and practicality mingle in the infinite dot in physics. Infinity often appears as a problem, yet even here it can inspire. Black holes may hide singularities, but they also create some of the most fascinating laboratories in the universe. The infinite expansion of space might suggest eventual solitude, but it also ensures that there will always be more beyond our reach, new mysteries waiting in the dark. Infinity's presence in our theories is not a flaw to despair over, but a signal that there is still more to uncover. It is an invitation to keep looking, keep refining, keep imagining. Infinity also has a role in how we think about meaning. A finite life lived within an infinite universe can feel insignificant, like a single grain of sand on a beach without end. Yet it can also feel precious. The fact that our moments are brief makes them glow brighter against the backdrop of eternity. Infinity gives context, but finiteness gives value. Without the endless, we would not feel the weight of the fleeting. In this way, infinity frames our experience, reminding us that our small span is part of something immeasurably larger. For many traditions, infinity carries spiritual resonance. It has been used to describe the divine, the eternal, the transcendent. Philosophers and poets have invoked it as a symbol of love, wisdom, or beauty that knows no bounds. Even outside religion, infinity can serve as a reminder of transcendence, a concept that lifts the mind above the mundane and into the realm of the vast. To say something is infinite is to acknowledge its resistance to confinement, its power to spill beyond edges. There's also something deeply human in our ability to imagine infinity at all. No animal, as far as we know, contemplates endless time or space. Birds migrate by instinct, but they do not wonder whether the sky has a boundary. Ants carry food in neat lines, but they do not ponder infinite regress. Humans alone carry this burden and gift, the capacity to reach beyond what can be seen or measured, to conceive of what has no end. This ability itself is a kind of beauty, evidence of imagination, unafraid of the impossible. Infinity also bridges science and art. In equations, it sharpens predictions. In poetry, it becomes metaphor. A mathematician might write of infinite series, while a poet writes of infinite longing. Yet both are circling the same idea, the endless, the unbounded, the beyond. Music, too, brushes against infinity in repeating motifs and endless echoes. A line of notes looping without conclusion can give the listener a sense of stretching beyond time. The arts remind us that infinity is not only a matter for calculation, but also a canvas for emotion. Even paradoxes reveal the beauty of the endless. Zeno's puzzles remind us that walking across a room contains infinite steps. Hilbert's Hotel reminds us that fullness can still accommodate more. The multiverse reminds us that our world may be one among uncountable others. These paradoxes unsettle because they resist resolution, but they also delight because they expand our thinking. Infinity is not there to be fully solved, but to be lived with like a horizon that recedes as we approach it. Its beauty lies not in answers, but in the act of pursuit. Perhaps the most calming aspect of infinity is that it softens finality. Endings in human life feel sharp and sudden, the final breath, the closing of a book, the last moment of a song. These are boundaries we cannot ignore. Infinity, by contrast, reminds us that on the larger scales, there may be no hard stop. Space may continue, time may stretch, possibilities may unfold without closure. Even if our lives are finite, they take place within a mystery that does not end. That thought can bring a strange peace, a reassurance that existence itself is not as fragile as the moments within it. Infinity, then, is a paradox not just of numbers, but of feelings. It can terrify with its enormity or comfort with its continuity. It can puzzle with its contradictions or inspire with its scope. It is at once beyond comprehension and intimately woven into our daily experience, from the act of counting to the vastness of the night sky. The beauty of the endless lies in this duality. It is both a challenge and a consolation, both the sharp edge of mystery and the soft curve of wonder. In contemplating infinity, we find ourselves stretched. We cannot contain it, but we can let it shape us as thinkers, as dreamers, as finite beings glimpsing the boundless. And in that glimpse, we discover not only something about the universe, but something about ourselves. That our curiosity, like infinity, has no end. Infinity has accompanied us throughout this journey like a quiet shadow, sometimes unsettling, sometimes comforting, always elusive. From the paradoxes of Zeno to the infinities inside black holes, from endless numbers to the prospect of infinite universes, it has appeared again and again as both a challenge and an inspiration. At times it has broken our equations, forcing physicists to rethink their theories. At other times, it has given us tools like calculus to turn the unending into something useful. And at every stage, it has stretched the imagination beyond the familiar, reminding us that the world we inhabit is far larger and stranger than what we see day to day. What is striking is that infinity is not confined to one domain of thought. It belongs equally to mathematics, philosophy, physics, and the human spirit. The mathematician sees it in endless sequences and uncountable sets. The philosopher encounters it in infinite regress and eternal time. The physicist meets it in singularities, horizons, and theories that collapse under its weight. And the poet, the artist, or the dreamer sees it in the endless sky, the eternal flow of time, and the boundlessness of love or imagination. Each discipline circles around the same vast idea, never quite capturing it, always aware that it stretches beyond. Infinity is also a mirror of our own limits. We are finite creatures with lives that span a handful of decades, with senses that perceive only a thin slice of reality, with minds that evolved to count sheep and seasons rather than grapple with the endless. Yet somehow we reach for it anyway. That reaching is what defines us. We may never fully comprehend infinity, but the act of trying is one of the purest expressions of curiosity. To chase infinity is to admit that our knowledge is incomplete, but also to affirm that it can grow without bound. There is a humility in confronting infinity. It reminds us of how small we are in the scheme of things. The observable universe already dwarfs us with its billions of galaxies. And beyond that observable bubble may lie an expanse without end. Time may stretch so far forward that even black holes fade to nothing. The smallest scales of matter may plunge into depths where space and time themselves dissolve. Infinity towers over us in every direction. And yet, rather than diminish us, it enlarges our sense of wonder. To know that we are finite is to also know that we live inside something immeasurably greater. Infinity also has a way of softening our perspective. Endings feel harsh in daily life. The end of a story, the end of a day, the end of a life. But infinity whispers that endings may not be absolute. Time may continue, space may stretch, possibilities may unfold beyond what we can see. Even if our own part is brief, the stage remains vast. Infinity does not erase our finiteness, but it places it against a backdrop so wide that it invites calm. It is important, too, to recognize that infinity is not always literal. Sometimes it is a signal that our theories are straining, that a deeper truth waits beyond. When Einstein's equations predict infinite density, it is not because nature loves infinities, but because our current picture of nature is incomplete. When quantum field theory spits out infinite energies, it is not describing reality, but asking for refinement. Infinity is a boundary signpost that says, the map ends here. The territory is still unexplored. Far from being a flaw, this makes it a gift. Infinity points the way to discovery. And even when it cannot be resolved, infinity inspires. It gives mathematics its elegance, physics its puzzles, and philosophy its riddles. It teaches patience because no one truly solves infinity. They only learn to live with it, to use it, to respect it. It teaches perspective because our lives, finite though they are, unfold inside a universe where the horizon always recedes. It teaches humility because our knowledge, however vast, will never encompass everything. Perhaps the beauty of infinity lies precisely in the fact that it cannot be contained. It will never be reduced to a single number, a single theory, or a single answer. It is not a destination we can reach, but a horizon that moves as we walk. The more we learn, the more it expands ahead of us. And that is not a failure. It is the point. Infinity ensures that curiosity will never be exhausted, that there will always be more to explore, more to imagine, more to wonder about. In the quiet of night, looking up at the stars, infinity is not frightening, but serene. It stretches in silence a canvas too vast to ever be filled. And in that vastness, our small lives find a kind of meaning. We do not need to hold infinity in our minds completely. It is enough to know it exists, to know that reality is larger than us, larger than our worries, larger than anything we can grasp. That knowledge can bring a strange peace, a reminder that even in the face of uncertainty, there is continuity, depth, and beauty beyond measure. Infinity, then, is not a problem to be solved, but a companion to live with. It is the quiet assurance that there is always more time, more space, more questions, more mystery. It is the endless backdrop against which our finite stories unfold. To encounter infinity is to remember that life itself is a brief spark within something boundless, and that spark is all the brighter for being set against the endless night. So as this exploration closes, it does not really end. The journey into infinity never could. The numbers will keep rising. The horizons will keep stretching. The riddles will keep deepening. And that is the beauty of it. The goal is not to conquer infinity, but to be reminded gently that it will always stretch beyond us. In that reminder lies a kind of hope. For as long as infinity remains, so too does the invitation to keep wondering, to keep imagining, to keep reaching toward the endless. The arrow of time keeps pointing forward, and as it does, entropy writes the universe's story across infinite pages. Each moment of order is precious, a spark, glowing against the endless drift toward equilibrium. Perhaps the deepest beauty of entropy is that it makes every instant unique, unrepeatable, and therefore all the more meaningful, even against the backdrop of infinity.